Okay, here's the bonding review. Alright, so we're on part A, short answer. In a non-covalent bond, electrons are shared equally or unequally, in the same question for polar covalent. So let's take a look at what we've got. With a non-polar covalent, we have two of the same atoms sharing electrons equally. Okay, so this is a non-polar, so the answer here would be shared. And in a polar covalent bond, we have two atoms that have different electronegativities. One's pulling the electrons closer to it, making it polar. So they are polar covalent is unequally shared. Okay, intermolecular forces are attractive forces that occur between or within. So let's take a look at the difference between inter and intramolecular forces. Intramolecular forces are those that are covalent bonds that holds the molecule together. Okay? Intermolecular forces, all those we've been talking about, dispersion forces, hydrogen bonds, dipoles, are the forces of attraction between two molecules. Usually two of the same molecules is what we're talking about. So intermolecular forces are those attractions that hold or cause attractions between two or more molecules. Intramolecular forces are always much stronger. Okay. VSEPR is used to predict the blank of molecules. Let's take a look at what VSEPR is. VSEPR stands for valence shell electron pair. So it's all about what's happening to the electron pairs, the valence shell electron pairs around the central atom. And the theory says that they repel each other because the electrons around the central atom are negative. They're going to repel each other, and they're going to cause them to be as far apart in space as possible. So if there are three places where there are electrons around the central atom, they're going to be equally spaced in three-dimensional space, three places apart. Same thing with tetrahedral if there's four. So VSEPR allows you to predict the shape. And what it says then is even though lone pairs take up space, they're going to repel electrons that are in bonds. So we need to count the number of places where there are electrons. Could be a covalent bond, it could be a double or triple bond, it could be lone pairs. We count those and determine what the arrangement of electrons would be, electron pairs would be, and based on that we can determine the shape. Covalent compounds. This is probably a poorly worded question. It probably should say covalent compounds have higher or lower melting points than ionic. So it's high or low versus what. And they do have quite a bit lower melting points than ionic compounds because they don't have the strength that the ionic lattices do. So they take less energy to cause the molecules to come apart. And the fact that a lot of covalent compounds are gases tells you that they've melted at very low melting points. Okay. Covalent compounds, unlike ionic compounds when they're dissolved, do not conduct electricity. If we go back and remember what causes electricity to be conducted, it's the movement of negative charges. But covalent compounds are neutral compounds. The electrons move within the molecule, but they don't move outside the molecule. If you remember, ionic compounds, once they're dissolved, allowing the positive and negative ions to float around, those are the moving charges which allow electricity to flow. So covalent compounds do not conduct electricity. Okay, it's telling us to classify the following compounds as ionic or covalent, so we need a periodic table to do that because, the ionic compounds start with a positive ion or metal. Okay, so hydrogen is a nonmetal, chlorine's a nonmetal. Covalent compounds are made from two nonmetals. So this is a covalent or molecular compound. Sodium bromide starts with a metal, positive ion, so it is ionic. Ammonium hydroxide, a little bit tricky because ammonium, if you remember, is a positive ion. It's a cation. So this is also going to be ionic. Ionic compounds start with either a metal or a cation, and the only cation or positive ion is ammonium. Okay, the NH bond is polar covalent. Which atom will be slightly negative and why? If we take a look at the table of electronegativities, we see hydrogen has an electronegativity of 2.1, nitrogen has electronegativity of 3.0, which means nitrogen's more electronegative, which means it pulls the electrons closer to itself, which is going to make it more negative. Okay, dispersion forces are due to the motion of electrons. And what dispersion forces says is that, electrons are always moving, and while something might be nonpolar, normally it's possible, just because of the movement of those electrons, that for an instant or a split second there might be more electrons on one side than another, causing a very temporary negative positive dipole. Okay, so it's a temporary, transient, unsymmetrical distribution of electrons. So dispersion forces are due to the motion of electrons. So the question of which has stronger dispersion forces comes down to fluorine or chlorine, which has more electrons, and chlorine has more electrons. And we can usually look at mass as an indication of how many electrons something's going to have, and chlorine has more. So we're not just talking about valence electrons here, we're talking about all electrons. So the more electrons, the more dispersion forces a molecule will have. Intermolecular forces, true or false, all molecules contain dispersion forces, and this would be true because all molecules have electrons, and if you have electrons, you have dispersion forces. Okay, dipoles are present in polar or nonpolar molecules. A dipole, if you recall, if you think about the water, the side that's more electronegative, either due to lone pairs or due to a more electronegative atom, is going to be more negative. The other side is going to be more positive. This creates a dipole, which is a separation of charge by a short distance within the molecules, causing attraction between molecules. So only polar molecules have dipole forces. Which molecule contains dipole forces? Well, it's only going to be whichever one is polar, right? So chlorine, Cl2, let's take a look at it, is nonpolar. Chlorine's going to pull equally, so it will not have dipole forces. But HCl, the chlorine is more electronegative than the hydrogen, so this will cause a dipole here. And which has a higher boiling point? Well, anything with a dipole, anything that's polar, is going to have a higher boiling point than something that's not polar. Okay, so chlorine and hydrogen are going to have low boiling points compared to HCl, which is going to have a higher boiling point because it's going to be attracted to other HCls. So I have nitrogen. I've got one of them. That's 5 electrons. I've got 4 hydrogens. Each has 1 electron. That's 4 electrons. The plus 1 tells me that I've lost an electron, so I'm going to subtract an electron. That gives me 8. So I always start off, put the central atom in place, surround it with the others. Whoops. A little skewed there. And assume single bonds. When I do that, I get 2, 4, 6, 8. So this works. I've got 8 electrons. Because it's an ion, I'm going to say it's got a plus 1 charge. Put the brackets there. This would be a tetrahedron, and it would be nonpolar. Alright, I got the phosphate ion. Phosphorus has 5 valence electrons. Oxygen each has 6. There's 4 of them. That's 24. The 3 negative tells me I have 3 extra electrons. That's going to be 32 electrons. Put phosphorus in the center. Surround it with the 4 oxygens. Assume single bonds to start. See if it works. Give everybody a full octet. When I do that, I then add up how many electrons I've used, and it's 8, 16, 24, 32, so this works. Put my brackets around this to show that the whole thing has a -3 charge. It's going to be a tetrahedron, and it's going to be nonpolar. Carbon has 4 valence electrons. Fluorine, oops, I don't know why this is going away on me, has 7 each, that's 28. So that's a total of 32 electrons. Put carbon in the center. Again, assume single bond, see if it works. Give everybody a full octet. Add up the electrons I've used. 8, 16, 24, 32, so that's good. It's going to be a tetrahedron because it's got the same stuff on the outside of a symmetrical molecule. It's going to be non-polar. SF2, S has 6 valence electrons. Each fluorine has 7 for a total of 14. That's 20. I'm going to give it sulfur in the center. Assume single bonds. When I do that, I'm then going to add up what I've used. 28 and 8 is 16, up to 18, 20. So I've used 20. So that's my structure, Lewis structure. If I build this, though, what I'll see is it looks like this, with the lone pairs up here. And so this is going to be a bent structure, and it's going to be polar because of those lone pairs. Okay, and then we have S. Sulfur has 6 valence electrons. Each oxygen has 6 for 12. Add those up, I get 18. I have S. I'm going to assume single bonds. Give everybody an octet. When I add them together, I get 8, 10, 12, 14, 16, 18, 20. I've got to get rid of a pair of electrons, so I'm just going to put a line through those. And now this oxygen doesn't have enough, so I'm going to take this pair here and move it inside. Okay, so I end up with using 8, 10, 12, 14, 16, 18, and I've got one lone pair here, so this is going to be a bent shape, and it will certainly be polar because of those lone pairs of electrons. Okay, C2F2. I'm going to have 2 carbons, each has 4 electrons. That's a total of 8. I have fluorine, each has 7, that's a total of 14. That's going to give me 22 electrons. Okay, so I'm going to do carbon and carbon. That's a non-polar bond. I'm going to surround it by the fluorines. Give everybody an octet, see what I've got. And I use 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I've only got 22. I'm going to get rid of, let's say, get rid of these 2 pair. That gives me 22. Now the carbons only have 6, so I'm going to move this pair into here. Get rid of that. This carbon is happy, but this still only has 6, so I'm going to move this into here. So I'm going to end up with C, triple bond, C with F's on the end. So this is going to be a linear molecule, and it's going to be nonpolar because I got the same stuff on the ends of a symmetrical molecule. Carbon dioxide. Carbon has 4 valence electrons. Each oxygen has 6 for a total of 12. So it's going to be 16 electrons. Put carbon in the center. Assume single bonds. Give everybody a full valence shell. When I do that, I use 8, 10, 12, 14, 16, 18, 20. Got to get rid of 4. Let's just get rid of those. Whoops. Get rid of those. Now this oxygen doesn't have enough. I'm going to move this inside here. I'm going to move these inside here. So I end up with C, double bond O, double bond O. And I've used the right number of electrons, so this shape is just 2 places around the central atom have electrons, so this is going to be linear, and it's going to be nonpolar. CH2O. Oops, let me go back. Alright, carbon has 4, each hydrogen has 1 for 2, oxygen has 6, that's 12. I'm going to put carbon in the center, surround it with the other atoms, assume single bonds to start, give everybody an octet. This should be lone pairs. Oops. Okay, I got 2, 4, 6, 8, 10, 12, 14. I only got 12. So I'm going to get rid of these, which look messy anyways, and move it in here. So I end up with using the right number of electrons, and I've got 3 electron domains around the central atom. So this is going to be trigonal planar. And it's going to be polar because the oxygen side is going to be more electronegative than the hydrogen side. I'm going to have a dipole here. It's going to be more positive. It's going to be more negative. So it will be polar. And that's going to